Well, good morning, everybody. Thanks for coming so early in the morning on our last class of week 3. Boy, after today's class, we'll be 1/3 of the way through the class. I hope everybody's getting settled and how to take the quizzes. So this quiz today is due Sunday, right? So you don't have that much time as before. Today's going to be kind of interesting. I'm going to finish up on the accidents. We're going to tie that together with the last part of the technical part of the avionics for aircraft. And we're going to introduce some pretty interesting concepts. We'll talk about atmospheric pressure. So atmospheric pressure for pilots is measured in inches of mercury. So if this was a long tube of mercury, then I were to say, well, how high could I go with that straw before the mercury would no longer be coming up? How high could I go? Well, I could go around 29.92 inches if we were in a standard atmosphere today, which I don't know. I don't know what the atmospheric pressure is today. So pilots use that. They use that 29.92. Don't drink the mercury. My granddaughter wants you to know that. Don't drink the mercury. So the other thing we're going to talk about is the Earth. Does the Earth look like this, like we think it looks? And, and the answer is no. The GPS thinks the Earth looks like this, thinks the Earth looks like that. They call it the WGS 84. You can see WGS 84. That's what the GPS thinks. And of course, the MSL, the sea level thinks the Earth looks like this. And it's kind of a dented, screwed up, and that's called the let's see, that's called the geoid. The geoid. So we're going to introduce different Earths because they're all different mathematical models that everybody uses, whether you use an iPhone or fly an airplane. So it's going to be an interesting morning, pretty busy. Same ground rules as always. You can interrupt me about something I'm talking about. Otherwise, I'll stay after class for office time if you want. And I'll be available Sunday night around 8 o'clock at night for those having a panic attack right before the exam, via email, not via Zoom, but via email. Okay, well, with starting it that way, my granddaughter said she might be available in the break for another demonstration of atmospheric pressure too. So let's go back and see where we were. No risk, no reward. They're kind of tying up the airplane, but we were talking about accidents, weren't we? And the accidents, let's see if I remember, were procedural for error, usually pilot error. Couldn't have to be pilot error, but usually. And engineered for design, something wrong with the design, like the 737 MAX, which flew, by the way, yesterday. We'll talk about that. The head of the FAA flew it. He's a 737 pilot. He's also an executive from Delta Airlines. Don't get me started. And then the third accident was a systemic accident, of which I'm going to give you an example of it this hour. We'll talk a little bit about how complicated automation can become for the pilot. This is just a simulator screen. I like this one because it kind of hits you and says, "Holy cow!" The pilot's got to be watching all that stuff all the time. Yeah, pretty much. There's a priority scan that he has to, But if he can't see outside, this is the pilot's world. It's a video game, isn't it? Sure. Today's standards, it's a video game. Unfortunately, a lot of pilots look at it that way, without seeing how serious they are when they forget the rules, the natural mathematical rules that they're flying under. So again, I don't mean to leave you with a shakiness of flying, but I do want to show you, I know we have journalist majors in the class, how difficult it is to get at the roots of the story and then to affect change in society. So it's to me, it's crucially important that we keep the checks and balances that the country was founded with, supposedly, ideally. Let's get those back, because once you lose a check and a balance, the system tends to go out of control one way or another, unstable, and then we don't find out the causes of these accidents. And automation is gonna make that problem probably worse. So we'll finish today. Let's see if I get my my trusty spotlight that I like. If I can get that working. These are the accidents we talked about. The Colgan flight, which was a procedural accident, too much icing, bad stall recovery. The Boeing 737 MAX, which is a design disaster, and hopefully it's going to be fixed and flying by next year safely. I don't know what they're going to call it. Uh, People might start demanding to know what kind of airplane they're getting into. I wouldn't be surprised. And today, this hour, we're going to talk about the ValueJet crash, which is a systemic accident. And then the second hour, after I introduce some of the complexity due to automation, after that, we'll look at an Air France Airbus. For those of you who still think, well, it's safe to fly Airbus, I want to destroy that. I mean, it's no safer or unsafe than anything else. So we'll look at an Air France accident that occurred flying from Rio de Janeiro to Paris at night. And of course, attitude is everything. For this, we either adapt or die out. I think that's not my rule. That's evolution's rule. So life is a continual process of change. And hope. All right, here's the ValueJet crash. It's a DC-9. Now the DC-9 is the Boeing equivalent of the 737. I mean, it's the Douglas equivalent of a Boeing 7. It's a very common DC-9 airplane. Best Air Force uses it for air evacuation for sick and wounded. So I've got a lot of flying hours on it, not as a pilot, but on it. So this was a civilian version. We're still trying to find out who to blame for this clause. It's a systemic accident, and that the procedures surrounding it were so complicated. For example, not only were the pilots underpaid at ValueJet, is a fly-by-night airline that started, but mechanics, ramp personnel, flight attendants, and we saw some of the outsourcing that occurred from the major airlines to the small airlines. Well, the small airlines were outsourcing to companies. I don't want to call them fly-by-night companies, but companies that we'd have no idea what their experience. Just formed it up. Someone formed the company. So you had people loading bags involved in the maintenance and putting things into the cargo hold that we don't know how experienced they were. The cheapest one was the one that they picked. And a lot of these companies were noted for pencil whipping some of the docks. That's called inverse Murphy's Law. Murphy's Law is things will happen, that bad happens will happen if they can. Inverse Murphy's Law is like going through a yellow light. Well, nothing happened that time. So I'll go through the yellow light again. So you keep going through yellow lights, and then you just make the possibility there that someone will sideswipe you at 50 miles an hour. So that's the inverse Murphy's Law. So we just skirt this a little bit over here. We skirt this a little bit over there. We skirt this procedure, that procedure. And next thing you know, you end up with a horrific accident. So this one, if you want to blame anybody, was a clueless manager in a cleanup visit. He saw these oxygen canisters. Now, oxygen canisters are the things that drop down from the ceiling in an airliner when you lose pressurization. The stewardess always says, put it on yourself first and then your kid, because you don't want to pass out. Well, that's never happened. You realize that in all the decades of flying that I know of, there has never been anyone saved by putting that mask on, because the pilots, they know they're going to get down as soon as they can. Anyway, these things are dangerous because they start a fire. They have a small explosion inside, and they generate their own oxygen. Right? It's an oxygen canister. So they're considered hazardous cargo. And this is the box from an airliner that was decommissioned. They carried red tags on them, but they weren't empty. So they should have been capped. They should have been capped so they couldn't have been set, but that never happened. And then they were in a box, and some manager came in and said, "Oh, we're getting an inspection from our Continentals coming in next week, our mother airline. And, they're going to inspect us." This is all in 1996. So it's before the Colgan accident. So he says, "Get rid of that box." So they pick up the box, they put duct tape on it, and then they say, "These are just empty canisters." Well, that's not hazardous cargo. If it's empty, it's not hazardous. So they put it in, and then they put it in with some tires, which was, again, a no-no. And then something set off one of the canisters, and then we had a horrific accident. It was hard for me to make this video because a lot of the reenactments show a lot of tragedy. I didn't want to show the tragedy. I just want to show the technical things that happened in this accident. It's really hard to watch this thing at all. So it took, after the accident, it took 5 weeks to ground it. The FAA came out as a proponent of the airline as opposed to a regulator. You'll see that in the video. And so 0 accidents. Try to see who to blame for this particular accident.
A SaberTech driver pulls up at gate G2 at Miami International Airport with ValueJet cargo for flight 592. Inside the boxes are 144 out-of-date oxygen generators loosely packed. A ramp agent places them around a large airplane tire. The pilots are unaware that they have a dangerous load on board. 30 minutes to go. The runway, the loose packing and unsecured cargo jolt one of the generators into action. It begins to heat up. 11 minutes to disaster. The plane taxis to its takeoff position. In the hold, the surface of the metal generator gets hotter and hotter. Soon the heat ignites the cardboard box and bubble wrap, and the blaze begins. 10 minutes to disaster. Flight 592 takes off from Miami International. Even though the hold is airtight, the fire is now blazing, sustained by the oxygen produced by the generators. 3.5 minutes to go.
What is that?
The sound heard by the crew is one of the tires in the hold bursting, just as it did in the lab test. To the pilots, the fire begins to eat away at the systems on board.
We got some kind of electrical problem.
The battery charge is kicking in.
We're losing everything.
The battery charger can't help the stricken jet as the fire is consuming everything in its path, including the control cables that run to the rear of the plane. Captain Kubek begins to lose control of the aircraft. The cabin floor burns and begins to cave in.
We need oxygen. We can't get oxygen out there.
They're going to be standing by for you.
So again, I wanted to point out that I just covered some of the the major details of this particular accident. The full story and why it's considered a systemic accident in detail is in one of the optional references for you to read. It's the reference from Atlantic or from the Harper's. I can't remember if it's Atlantic or Harper's magazine that's in the reading file. When you have time someday, that's where I got the information for this particular video and portion of the lecture. So notice what the airlines do. That ValueJet kind of fly-by-night airline bankrupt, they had bankruptcy, came back as another AirTran, right? And then in 2014, they merged with Southwest somehow, and who knows how they're related to Southwest now. But you can see how they just kind of regenerate. But the structural thing of how can we eliminate this type of horrific accident isn't addressed. In fact, the FAA made things worse. You'll see David Hinson, who was the head of the FAA, was an aviation proponent, was defending the airline, even at the accident site, right? So the deep irony is that the fixes to systemic accidents that tend to automate the process, that those fixes reduce the accident rate. But the paradox is that they pretty much guarantee there's going to be another accident when we don't know what the cause is. They're still trying to find out who caused this accident. They blame two maintenance guys. Again, SaberTech was hiring guys off the street. Who knows what their background was? They blame two maintenance guys. One escaped, and they think he's in Bolivia somewhere. But give me a break that the mistakes were made at the high levels of management who allowed this type of system to evolve without checks and balances. And of course, then it reflects back on the FAA. So this is what happened to the FAA, and the results of this accident were known about 3 or 4 months before the Colgan accident that we started with this thing with the icing. And the results of this accident were well known and were glaringly ignored by the Colgan accident, which was a procedural error in itself. So,
Relying on the FAA to ensure that all carriers fly safely has its limits. The FAA has less than 4,000 inspectors responsible for overseeing the safety of about 25,000 commercial flights in the U.S. every day. The crash of 3407 has raised anew questions about how well the FAA is doing its job. Questions that had previously surfaced in the mid-90s with the rapid rise of a low-cost airline called ValueJet. As ValueJet grew, so did its safety troubles, yet the FAA failed to heed warnings about repeated problems. Mary Schiavo was the Inspector General of the Department of Transportation at the time.
Instead of hitting them with violations, they were propping them up. My office said, whoa, wait a minute, this doesn't pass the smell test. When you've got an airline having this many problems, the FAA isn't doing proper oversight.
Hopes are fading now of finding any survivors from the crash of a ValueJet DC-9.
Then, in 1996, ValueJet Flight 592 from Miami caught fire and crashed into the Everglades.
Reportedly, the FAA says there were 109 people on board.
The Secretary of Transportation and the head of the FAA went into protective overdrive. The Secretary of Transportation flew down to Miami and stood in the Everglades, literally on the watery grave of 110 people, and said, ValueJet is a safe airline.
I want to emphasize that I have flown ValueJet. ValueJet is a safe airline, as is our entire aviation system.
okay, I got to stop this now. This is from today's Bloomberg News. Today's Bloomberg News about the 730 MAX that flew yesterday. The test flight yesterday was by Steve Dixon, the head of the FAA, right? And he's a 737 pilot, and he's showing you that, hey, I can fly, it's going to be safe, right? Well, he had a Boeing test pilot at his side, took the training course that is expected to be approved. Dixon's plane lifted from the Seattle Boeing field shortly before 9 a.m. local time. Afterwards, the former Delta airline executive is expected to brief reporters on the agency's progress, which occurs today. The former Delta X is the head of the FAA. Okay, here's the head of the FAA after ValueJet 1996. This is what, almost 25 years later. You still got airline executives at the head of the regulator. That's called regulatory capture. You see what I mean? How regulatory agencies are captured by, oh, geez. All right.
I was very angry because they knew that airline was troubled. Why? Because I'd been called into the Secretary of Transportation's office. The FAA administrator knew we were down there looking. We had presented some of our findings already.
Were they lying to the public?
I think so.
Why?
Because the FAA protects airlines.
The FAA's response to ValueJet exposed an inherent conflict in the agency's original mandate.
The Federal Aviation Act of 1958 gave the FAA two primary missions. One, safety. Two, promote aviation. In no particular order.
After the ValueJet crash, Congress, under public pressure, removed promotion from the FAA mandate. But a closer look at the legislation tells a different story.
There's a footnote in that legislation before Congress. And the footnote says, although we're changing the terminology from promote to encourage, we do not intend to change the way we do business. This is a change for the public consumption, and we're not changing how we work at the FAA. It was simply a sleight of hand.
Nick Sabatini worked inside the FAA for 30 years and was the head of aviation safety from 2001 through 2008.
I never did see that there was a conflict. I could easily compartmentalize. If I'm encouraging you to do better, I'm not encouraging you to necessarily grow your business in terms of promoting aviation. The promotion was promoting aviation safety as we saw it.
Under Sabatini, the FAA forged a new regulatory approach with the industry called partnership programs. The FAA relied more on the airlines to self-report problems and help identify emerging safety risks.
We need to learn what those unknown risks are out there. Who is best positioned to know what risks they see every day? It's people who are operating the system and have their hands on the system every single day.
But critics say the FAA's collaborative approach went too far. A policy directive in 2003 called the Customer Service Initiative identified the airlines as the FAA's customers and encouraged the industry to challenge the decisions of FAA inspectors.
The problem, though, with the Customer Service Initiative, the way it was pushed, the way it was implemented, the way it was communicated to the workforce, it sent the wrong message. It sent a very bad message to the industry. It sent the message that, look, I can cut a deal. And all you had to do was make a phone call to, somebody that you became friends with over the years and request reconsideration, and it would be taken care of.
Both the FAA and industry say their success working together is borne out by statistics, that flying today is safer than ever. Prior to the crash of 3407, it had been 2.5 years since the last fatal commercial airline accident in the U.S.
In those intervening years, the United States air transportation system transported 2 billion people, maybe a little bit more. That is the equivalent of having transported the population of the United States more than 6 times without putting a scratch on anybody.
But in the airline industry, there's a common expression that the absence of accidents doesn't necessarily mean you're safe.
Inverse Murphy.
When people say that, what do they mean?
Well, what you really have to look at are the thousands of things that lead up to the accident in the first place. Human beings will make a lot of little mistakes that serve as a warning before a big mistake occurs and a big consequence. So what it means to really be safe is to be focused on those little warning signs and catching them early. It's only when we miss a bunch of those warning signs that we have a tragedy.
The question in the wake of 3407 is whether the FAA missed warning signs about safety problems at Colgan Air. As early as 1998, Colgan's problems were evident when the company began to grow as a regional airline. Colgan was supposed to upgrade its operations to meet the same level of safety as the major airlines. But in a letter from Colgan to the FAA obtained by Frontline, the company acknowledged it had to make significant improvements in order to meet the more stringent safety standards known as Part 121 regulations. The company committed to making substantial changes in pilot training, record-keeping, management, maintenance, and safety audit systems. The letter was signed by company founder Chuck Colgan. But 7 years later, in 2005, Colgan was still not meeting its regulatory requirements, says Chris Monteleone, who was a lead FAA inspector overseeing Colgan's growing operations.
There were not enough managers. There were not enough check airmen. There were not enough maintenance personnel.
Were they just overwhelmed?
They were acting as if they were overwhelmed. They couldn't control their business, the safety part of their business.
Monteleone says he took his concerns about Colgan to his office manager at the FAA, recommending enforcement actions against the company. But his manager, he says, was getting pushback from company president Mike Colgan.
Mike Colgan would call, or in some cases, it got to the point where he wrote about me to the office manager. And the office manager one time told my team, he said, Mike Colgan is a friend of this office. And that was the message. I mean, it was like, well, we already knew it, but he felt the need to reinforce it.
Did you, in the course of that, feel pressure not to stop that growth? In other words,
absolutely.
Were you seen as a roadblock?
Oh, absolutely.
The FAA office manager says he does not recall making those statements. But 3 years later, there were still problems when Colgan got another big contract from Continental. Colgan began flying a new airplane called the Q400, the type of plane that would crash in Buffalo. Did you get the sense that everybody was a bit overwhelmed by this airplane?
Yes, because there was a lot of growth. It was almost the same thing that was faced with the 2005 expansion, with this 2008 expansion of the Qs. There was a lot of growth, a lot of growing pains suffered by the company as well as the crews, because it was new to all of us. None of us had ever operated this airplane before.
In February 2008, Colgan began flying passengers on the Q400. But the FAA was soon concerned that Colgan pilots were having trouble flying the airplane. There were reports that pilots were exercising poor judgment. And Colgan was short on check airmen or supervisory pilots for its Q400 fleet. So I guess were you a little surprised when they came to you and said, we want you to fly and supervise this crew?
Very surprised.
Why was that?
Because I'm not type rated in the aircraft. I'm not qualified in the aircraft. I had never flown the aircraft, and I didn't even know what the limitations of the aircraft were, let alone it was very unclear as to exactly what we were supposed to be doing.
So did you have the sense they just wanted a warm body in that seat?
Yes.
There were other warnings about the safety culture at Colgan in 2008. In this NTSB file, we found a case that alarmed the FAA. It involved the actions of a Colgan captain on a flight out of New York City. The first officer on the flight was Ben Coates. It was Coates' job to calculate the weight limit on the flight, and his calculations showed the plane would be too heavy to fly. And you say to the captain, Captain, we're even more overweight than we thought. What do you say?
Well, he said, well, why don't we just count 3 of those adults as children?
Really?
You know, just mark them down on the sheet as children, and that'll put us underweight. That's what he suggested.
Coates says he refused, and the captain took the weight manifest from him. Only after landing did Coates discover what had happened with the manifest. So when you looked at the paperwork, which had all the information on the weights and balances for the plane, what did you see?
Well, I saw it had been altered. My math had been altered. It had been changed so that our plane would no longer be overweight.
He made the limit higher
exactly.
So the plane would fit.
Yes.
And what you ended up with was a very heavy aircraft.
Yes, a very hard to fly, hard to climb at least airplane.
Unsafe, illegal airplane.
Yes.
Dangerous.
Yes.
Very dangerous, actually.
Very dangerous.
Coates felt it was so dangerous that he filed a complaint with the FAA. The case landed on the desk of the agency's top regional attorney, Loretta Alcalay.
They were shocking allegations of violations by an airline captain, falsifying a load manifest to indicate that there were fewer passengers than there actually were, and flying over gross. So it was a pretty outrageous case.
Based on its investigation, the FAA revoked the captain's license.
And I think the biggest issue really is, what did Colgan do? I mean, what did Colgan do when we revoked one of their pilots? I mean, that's really the question. What did they do? I mean, you would think that they had done a top-to-bottom review about what was going on.
But what Colgan did surprised Alcalay. The company testified at an appeal hearing in support of the captain. And DeVenis, Director of Operations.
Yes. Well,
testifies that you're a problem, right?
I think he did, yeah.
And the captain?
Model pilot.
Whose model?
I don't know. Not my model. But apparently Colgan's model, according to the Director of Operations. And he said that under oath in an NTSB hearing. Which raises the question in my mind, how come Colgan isn't under investigation? Why do they still have an air carrier certificate? And especially if their Director of Operations is, you know, officially supporting an unsafe captain and not supporting a first officer who's trying to scream safety.
I don't understand why they would come in and support him. I mean, it was breathtaking in its horror at the time. I mean, it was horrifying.
So that, to you, presented a whole host.
So, if I could point out a couple of things, the captain of that had a lot of options. He could have offered people to get off the flight more money and come back at a later flight. That probably happened to many of you. It happens to happen to me a couple times. Or he could have defueled the airplane. If he had excess fuel on the aircraft, he could have defueled it. There were options open to him that he could have taken. But you see the dedicated people at the FAA who are in the technical part, the pilots, the engineers, the maintenance people that are working there, they often are butted up in their own organizations at the higher levels by managers who are under influence, excessive influence, by the people that they're supposed to be regulating. That's a serious problem. And those are, I know we have a lot of business people in the class, and you'll see that. You know, you don't want an organization where the engineering and the technical and the maintenance people are confrontational with the upper management. You want an organization where they are as a cooperative relationship between engineering, pilots, the technical people, and the upper management. And sometimes the government makes it worse because of the lack of check and balances or by regulatory capture. So let's go back, if I can. Let's see. So that kind of finishes the accidents. What I wanted to talk about now is automation and some of the buzzwords that are used, and then we'll look at a final accident to kind of tie together this whole piece on the different types of accidents and automation in airplanes. So what I've got circled in red here are the buzzwords that are often used. I don't expect you to understand in detail what I've got shown here, but what I would like you to do is to look at the, if I get my spotlight working again, look at these red things that I've got. So in other words, avionics means aircraft electronics. It's analog and digital electronics, the displays, the iPad displays that the pilot now sees. And then, of course, we often use the word guidance, navigation, and control. So the letters G and C are very common. I mean, guidance, navigation, and control. And each of these letters has meaning. G, for example, guidance means how does the pilot get situational awareness? How does the ground help the pilot, and how does the pilot help the ground give situational awareness of what's happening relative to what I'm trying to do? You also hear the words PVT a lot, PVT, and that's part of navigation. Navigation is position, velocity, and time. And all of those are models. As I told you, the GPS uses an ellipsoid. MSL is relative to a geoid. So the atmosphere itself is a model. The atmosphere is a mathematical model. And then you get these buzzwords called like fly-by-wire or FMD, of the maintenance display, the pilot displays and how it's presented to him. So that's all. I'm just showing you some of the buzzwords so you're familiar with the buzzwords and not necessarily how each of them is implemented or works in the cockpit. Except for these two instruments. This top one on the right is called the attitude indicator. And when you want to, this is the key thing. When the pilot loses everything else, he'll go, if he can't see outside, he'll go to his attitude indicator. Because this is the landing gear image right here. And then that's he sees the horizon out here. So he sees that he is in a right turn, right? And this is his pitch angle. If he's looking at the attitude indicator and it starts pitching like that, it says he's climbing. If it goes the other way, it says he's descending. And if it rolls, so it gives him an attitude as if he's looking outside. And on the bottom, the horizontal situation indicator gives him his magnetic heading, not his true heading on a map. All right, we'll talk about that next hour, but it gives him his magnetic heading because his magnetic heading comes from a probe that's out on the wing, a magnetic sensor, right? And he doesn't need any help to get that information from the ground. So situational awareness is what guidance is and is given to him by these two instruments. Now you might ask the question, what happens if the pilot's flying straight up or straight down? Hopefully not straight down, but what do these instruments show? And they normally go dark. Sometimes they'll just rotate and go dark because that's how gyros used to tumble. When I learned how to fly, in the old instruments there were gyros, and when you went straight up, the gyros would tumble. So that sometimes they will tumble or make these instruments go dark because heading and attitude is undefined going straight up. You're just going to see a blue, but you don't know what your heading is because it's undefined, or a roll angle. You don't know what your roll angle is. What's my roll angle, right? It's hard to define. So the attitude, the pitch angle, and the roll angle, if you're not going straight up or straight down, is shown by the attitude indicator. Magnetic heading is shown by the horizontal situation indicator. And if the ground is sending you information, then you'll have additional bars for guidance from the ground. So these are the cockpit displays, and they give pilot his situational awareness. And then at most airports, they have an instrument landing system that allows you to land. It's very complicated, expensive systems that exist on the ground. And they're usually at the big airports. So Los Angeles will have one. San Francisco will have one. Chicago. They'll have instrument landing systems. They're very expensive, and they run these bars that make it kind of a video game for the pilot to fly. The key thing, the most important thing, because one of the test questions I see is going to be the difference between the aircraft magnetic and aircraft true course. I'll cover that this hour or next hour. But the key thing is when the pilot needs to know his altitude. And the pilot gets his altitude from what's called an altimeter, and the altimeter carries a mathematical atmosphere. So if I were to show you, this is the altimeter over here on the top right, and right now it's reading 530 feet. So does that mean the pilot's 530 feet above the ground? Not necessarily. In fact, probably not, because the pilot has to pick his reference. Remember at the start of class? At the start of class, I took with a straw, and I said, air pressure is pushing down on it. Air pressure, how far up could I go if this was mercury? and I could go up 22.92 inches. Well, that's what's measured by an altimeter. That altimeter measures outside pressure, but it's calibrated with a mathematical atmosphere. So the pilot selects the reference. The pilot selects where 0 feet is mean sea level. He selects where sea level is. So, I mean, where does he get that information from? Well, if he doesn't know anything else, he'll put 2992 in there. He'll put a standard atmosphere. But normally, he'll get a weather report, and the tower, someone will call him and say, the altimeter setting is 2984. So he will set the reference when the altimeter would read 0 feet. He'll put that reference in there. Then, with that correct reference in, he can read this and he say, oh, I am 530 feet above mean sea level. Well, San Luis Obispo is 212 feet above mean sea level. So what if I'm looking at this in my cockpit at San Luis Obispo? Well, that means I am about 300 feet above the ground. From 212, 3, 4, 520, I'm about 310 feet above the ground. I have to have that in my head. I have to know the field elevation and subtract my reading with the correct altimeter setting set in here. That's crucial because if you're landing and you can't see outside, you need to know exactly how high you are above the ground. So the altimeter displays in thousands and hundreds of feet the height above mean sea level. It never displays height above the ground. Height above the ground is computed by your mental abacus called the brain up here. Now, if the altimeter measures, if it measures 2982, suppose it measures 2982 and it's set at 2992, then there's a 1 inch difference. A 1 inch difference in mercury, a 1 inch difference from up high is about 1,000 feet. So when the altimeter measures 2982 and he has 2992 set in, he'll think he's 1,000 feet. This altimeter will read 1,000 feet. So if the aircraft is in the standard atmosphere, a reference value of 2992 should be, so if he's in a mathematical standard atmosphere, that mathematical atmosphere was fit. Let me show you how that was done. If I can find it. It was done, oh yeah. So if you can see that, this is the mathematical standard atmosphere that came out around 1960. And done by the Geophysics Research Lab at Cambridge, Air Force Cambridge Research Center. And here's what it looks like. There's the height. This is a mathematical fit to the atmosphere of the Earth, right? So at 0 feet, I guess I'm going to need my my annotation so you can see it. So at 0 feet here, notice the altimeter setting in inches of mercury is 2992. So if you're flying in a standard atmosphere, you would put 2992 in. And look at what happens if you're 100 feet high. If you're 100 feet high, it's almost 2982. 200 feet is 297, 296. And you're at 1,000 feet, you've lost an inch of mercury pressure. And so it's not exactly a 1 inch, but you can use 1 inch for this class purposes. So from 2992 to 2982, you'll gain 1,000 feet in altitude. And of course, if you increase pressure, then you're going the other way. The altimeter will read this way. So that's how that works. That's how that works. And I got a video that I made that I think explains that, and this will take us very close to break. So let's review the altimeter since it's so important. I should mention, if you're way up above any mountains, if you're up above the mountaintops, then everybody sets 2992. Everybody that's flying sets 2992, because we don't really care what your actual height is. You know you're above the mountains. You just want to keep separated from each other. So they give you a flight level. You fly at 32,000 feet, 34,000 feet, just to keep away. But at low level, when you're close to the ground, then you have to make sure that you have the correct value set in, because 1 inch of mercury pressure gives you about 1,000 feet indicated. And you want to make sure when you touch down, you have the correct field elevation read on your altimeter. Here's a brief review of that. An aircraft altimeter is calibrated to carry a standard mathematical atmosphere. That atmosphere changes 1,000 foot for every measured inch of mercury decrease from some reference that's dialed in to the window of the altimeter. An aircraft altimeter measures barometric atmospheric pressure relative to a selected reference for 0 feet at 0 feet MSL. The selected reference is entered as inches of mercury, 29992 for a standard mathematical atmosphere. The atmosphere is calibrated to indicate plus 1,000 feet for every inch of mercury decrease in measured pressure below.
So let's suppose this ruler is an altimeter, a barometric altimeter. And what a barometric altimeter does, like this ruler, is it carries a calibrated atmosphere, a mathematical atmosphere in it. And that atmosphere is calibrated such that at 0 feet to sea level, I will measure 29.92 inches of mercury. In other words, that's the height that a mercury will rise if you had a mercury tube at 0 feet in the standard atmosphere. So if the pressure is standard in this mathematical atmosphere, 2992, the altimeter would read 0 feet. If, however, the altimeter reads 2892, 1 inch less, 1 inch is about 1,000 feet of increase of altitude. So as the inches decrease, if the altimeter measures 2892, it will read 1,000 feet. The big hand will make one, just like a clock, it'll make one big circle and read 1,000 feet. If, on the other hand, it feels 1 inch bigger than 2992, then it will decrease 1,000 feet from its reference of 0 feet. So here it's reading 0 feet at 2992 in the mathematical standard atmosphere. The question is the atmosphere mathematically, is the atmosphere that we're in a mathematical atmosphere? So I went out to Morro Bay and I got some water. It's a little dirty out there, but I think it's still drinkable. Anyway, what I saw is that at sea level, you can see at sea level, the pressure was 2892. So it's a low pressure day. That normally means the weather's going to be bad. Normally low pressure is associated with bad. So if I took my altimeter out there to Morro Bay and left it assigned at 2992, if I left this as the reference, then the altimeter would go to 2992, and at Morro Bay, which is at sea level, right? That's where the sea level is, it would measure 2892, but because the reference is set at 2992, it would indicate 1,000 feet. So say I was flying. What if I was flying in the clouds and I said, oh gee, I need to descend and see where the base of the clouds are. Maybe the base of the clouds are 500 feet. So I put the airplane in a descent because I'm indicating 1,000 feet on my altimeter, and I put it in a descent. What would happen? Well, I just went right into the drink. Oh my goodness. I don't know if I could find myself. I fell in there somewhere. Okay, so pilots remember this by saying, if I'm flying from high pressure to low pressure, from high to low, look out below. Because you might think that you're going to clear the mountaintop. You might think you have 1,000 feet above that mountaintop or sea level. So, but when you decrease that clearance to what you think is still positive 0, you're going to fly into the ground. High to low, look out below. So what happens, well again, if I were to look at this and say, oh man, that doesn't look good. So suppose I went back out there and that was sea level now. This is sea level day. Now it's a little different. And now I leave my thing at 2992, and I can see if this is actually sea level, then when I read 2892, I will be 1,000 feet. I will be 1,000 feet above the sea. But what happens if it's a high pressure day? If it's a high pressure day, like this, the pressure at sea level is going to be 3012. Suppose the pressure is 3012 on a high pressure day, and I leave 2992 set up. I think, I leave 2992, I think, at sea level. Well, now, when I read 3012, I'll think that the altimeter will be reading 1,000 feet below sea level. So, if it's a high pressure day, I'll read, and I read 3012, and I think that is, if I have 2992 dialed in, but the pressure is actually 3012, I will the altimeter will read low by 1,000 feet. Now it's telling me I'm too low, so I would want to go up and get rid of that 1,000 feet and come up to at least here. So when I'm at 0 and go up to here, when I read 2992, I will actually be 1,000 feet above sea level. So I will be actually higher than my altimeter reads. So from low to high, enjoy the sky. So this is when you fly into high pressure, which is good weather, then you'll be higher than you think you are with the altimeter reading set. Of course, the best thing is to have the altimeter set correctly. If you set it, no matter where you are, if you set it correctly at the right value for sea level, then your standard mathematical atmosphere, which is calibrated in the altimeter, will tend to match the actual atmosphere that you're flying in. Okay, hope that helps. Good luck. I want to say good. Not bad. Not bad.
So it's break time. My granddaughter's gonna give a demonstration. Don't drink the mercury, and I'll see you in 10 minutes. See you in 10 minutes. Okay, this is a demonstration of air pressure using mercury. That's mercury. Okay, so show how mercury works if you.
So this is actually chocolate milk, Grandpa.
Oh, okay.
And it's just we're using it instead of mercury. So if we would have it, it would be like 30 inches if it was mercury.
29.92 exactly, but almost 30. That's very good.
Yeah.
Yeah, it was right. Now you're gonna drink that mercury? You don't drink real mercury.
Yeah, don't drink real mercury.
Okay. Yeah, don't drink real mercury. Okay, so again, I'm going to show you a lot of them trying to make pilots out of you, but what I want, my goal here is to tie all these accidents together with the concept, with the idea that a lack of fundamental mathematics, of fundamental equations, is what's at work in causing a lot of these accidents. We tend to become procedure oriented. I hate math, right? But at the base of it, we're all dealing with virtual models in almost everything we do. So this is an approach. Again, let me get my my trusty spotlight here. This is an approach that a pilot flies. He starts out here somewhere, and it's like a video game in height and in the lateral direction. He gets bars in the cockpit that tell him how far he is from this course that's generated from the ground. Now, these are all true courses. In other words, they're represented with a map of true course on the Earth. But he's got magnetic information in the cockpit, so that conversion has to occur. So this is called an ILS, an instrument landing system. It has a very complicated, expensive, and monitored system by the FAA. The pilot has to fly, and it's usually only at big airports. Now, how is this changed? This is how the hub and spoke system worked. Everybody flies to the big airports, fly your little puddle jumpers to the smaller airports, like San Luis. Well, when satellite navigation came in, when GPS came in, now GPS, as far as pilots are concerned, you could call it WAAS, which is wide area augmentation. Those carry extra satellites for increased accuracy. And you might hear, instead of ILS, you'll hear LPV, localized performance with vertical guidance. So this ground-based instrument landing system, the pilot flies what's called a precision approach. And a precision approach takes the aircraft down to 200 feet above the ground. We saw how important it is to know where the ground is. Well, these GPS, WAAS, or LPV approaches, whatever you're going to call them, they're not the same. They're a little bit different, but they're all satellite-based. You can go to 400 feet instead of 200 feet. So if your weather allows you to see the runway at 400 feet above the ground, you can land. Now, why is that better than the instrument landing system? Well, because it doesn't take any equipment other than the GPS receiver. I could fly these WAAS approaches and GPS approaches anywhere where there's a runway big enough. So I can fly all over the country, basically, now, instead of just the big hub and spoke airports. So that's why we have smaller airplanes now that tend to be full, as opposed to big airplanes 2/3 full. So the hub and spoke has been modified now because of satellite navigation. That's what I want you to pretty much remember. Here's what shows you what the video game looks like, and you'll hear some of the pilot talk advantages of how it works.
Unlike a non-precision approach, LPV allows you to get within 1/2 mile of the runway and as low as 200 to 300 feet.
One of the major benefits of the WAAS LPV system is the superior flight crew coordination and situational awareness. Once again, our pilot, Dean Smith.
It's a very seamless operation for us as a flight crew. There's less crawlouts, there's less altitude selecting, less altitude you can bust, and a much easier approach to fly. So with the reduction of procedure turns, as in all GPS approaches, with the lower minimums and the reductions of step downs, it's a very valuable tool for us to have in our toolbox.
Traditionally, ground-based landing systems have been the only method for low-visibility approaches. Many business aircraft, however, are operated from airports without ground-based systems and are restricted to using non-precision approaches. If your aircraft is equipped with WAAS and LPV, you have many more options to get to where you're going safely and efficiently. There is a common misconception in the industry that WAAS and LPV are one and the same. However, they are two completely different systems. WAAS, or Wide Area Augmentation System, was developed by the FAA to augment GPS to improve accuracy. Put simply, it is a corrected GPS. It is accurate to about 1 meter of your actual position. Combined with LPV, it can get you into more airports in a more direct manner. Without LPV, WAAS is just nothing more than an accurate sensor. LPV, or Localizer Performance with Vertical Guidance, gives you an enhanced database in your FMS GPS and allows ILS-like approaches at airports that do not have an ILS or ground-based system. LPV approaches allow for minimums to be as low as 200 feet. If LPV is not available at the airport you are traveling, they likely have an LP approach available. LP, or Localizer Performance approaches, provide precision lateral guidance using the enhanced accuracy WAAS provides.
Okay, now I'm stopping this to show you he's up at a very high altitude. The altimeter here is reading around 7,000 feet. The altimeter setting over here had better be correct, right, if he's in bad weather. Because he wants to know his height above that 7,000 foot altitude exactly when he's in the weather. So this is the attitude indicator and the heading indicator all combined in one instrument called a HUD, heads-up display, and he's flying it with a satellite approach down to in a very high, low-density altitude aircraft.
This particular example, an LP approach into Telluride, Colorado, allows for lower minimums of an additional 460 feet for days when the weather is less than perfect. The FAA is no longer installing or repairing ILS systems, which makes WAAS with LPV an ever-growing need for your aircraft.
Now, the last thing that he said is not true. The FAA is still maintaining instrument landing systems at the big hub and spoke airports. It is. The ILS, don't forget, is a large FAA-run.
Unlike a non-precision
system.
approach,
it's a large FAA system that allows precision approaches. These satellite-based navigation systems are non-precision, so the minimums are a little bit higher. But the thing is, you could fly them anywhere in the country legally. So satellite navigation comes from GPS. And if you're flying, you have what's called Wide Area Augmentation System. In addition, you have GPS on your cell phone, right? You have GPS here, but they have WAAS GPS. And if you buy a Garmin receiver, you probably have WAAS also. Those are non-precision approaches, but you can fly at every airport that has a runway suitable for landing, which is amazing, right? Amazing. I looked at the chats over the break, and someone said, "Oh, you started class early." I know I don't. I start class at 10 after 9. at 10 after. But what I do is I sometimes prepare preliminary things so I can play with the thing and get it set up while something is going. So if you show up early, you might see something useful or something I think was funny, but it's not class time. If it's testable, it will be covered during the class hour, not before. But I usually start a little bit earlier just to make sure I'm all set up right when class time. Good observation. I'm sorry that was some confusion on that. All right, so here's the thing. I know not many of you are Boy Scouts or Girl Scouts, but if you were, or if you were a pilot, even pilots today, this is called a sectional chart. That's a sectional chart, and this is how you learn how to fly. You learn how to fly at a sectional chart. So somehow, this takes this Earth, a real round Earth, right, and puts it onto a chart. It looks like this one, and here's San Luis Obispo Airport right here. I can only go so far. This is at San Luis Airport. But it's got very complicated, and a good part of pilot training is learning how to read one of those sectional charts. So this is going to explain how they obtain that sectional chart and why it's still useful today. Because even the pilots that fly with iPads and basically use this type of chart. Sectional chart is what's called a Mercator projection. And this is what a Mercator projection actually is.
I'm gonna have to cut it open. In order to get this globe to look anything close to a rectangle lying flat, I've had to cut it in several places. I've had to stretch it so that the countries are starting to look all wonky. And even still, it's almost impossible to get it to lay flat. And that right there is the eternal dilemma of mapmakers. The surface of a sphere cannot be represented as a plane without some form of distortion. That was mathematically proved by this guy a long time ago. Since around the 1500s, mathematicians have set about creating algorithms that would translate the globe into something flat. And to do this, they use a process called projection. Popular rectangular maps use a cylindrical projection. Imagine putting a theoretical cylinder over the globe and projecting each of the points of the sphere onto the cylinder surface. Unroll the cylinder and you have a flat rectangular map. But you could also project the globe onto other objects, and the math used by mapmakers to project the globe will affect the way the map looks once it's all flattened out. And here's the big problem. Every one of these projections comes with trade-offs in shape, distance, direction, and land area. Certain map projections can either be misleading or very helpful depending on what you're using them for. Here's an example. This map is called the Mercator projection. If you're American, you probably studied this map in school. It's also the projection that Google Maps uses. The Mercator projection is popular for a couple of reasons. First, it generally preserves the shape of countries. Brazil on the globe has the same shape as Brazil on the Mercator projection. But the original purpose of the Mercator projection was navigation. It preserves direction, which is a big deal if you're trying to navigate the ocean with only a compass. It was designed so that a line drawn between 2 points on the map would provide the exact angle to follow on a compass to travel between those 2 points.
Okay, so if I was here's San Luis Obispo, and here's Santa Maria right here. So if I was to plot a course, I would lay a ruler on there and then look at the angle, that angle like that, and then that would be my true course. So if that's 360 degrees, maybe 340 degrees or so would take me from Santa Maria to San Luis Obispo, and I do that with a ruler and a map. Or I'd ask the computer to do it for me if I had an iPad. But that's what he's talking about.
If we go back to the globe, you can see that this line is not the shortest route, but at least it provides a simple, reliable way to navigate across the ocean. Gerardus Mercator, who created the projection in the 16th century, was able to preserve direction by varying the distance between the latitude lines, and also making them straight, creating a grid of right angles. Something happened in the...
Okay. So the latitude lines are these hash lines over here. These are the latitude lines. The longitude lines are the vertical ones. Okay. So the distance varies from the latitude lines on the Mercator projection. Okay, so you would always, if you were going to actually measure distance with a ruler, you wouldn't want to measure the distance between the latitude lines, right? You have to be careful how you measure distance and convert it with a Mercator projection.
The late 60s that would change the whole purpose of mapping and the way that we think about projections. Satellites orbiting our planet started sending location and navigation data to little receiver units all around the world.
Today, orbiting satellites of the Navy Navigation Satellite System provide round-the-clock, ultra-precise position fixes from space to units everywhere in any kind of weather.
This global positioning system wiped out the need for paper maps as a means of navigating both the sea and the sky. The Mercator projection, that once vital tool of pre-GPS navigation, was shunned by cartographers who now saw it as misleading. But even still, most web mapping tools like Google Maps use the Mercator. This is because the Mercator's ability to preserve shape and angles makes close-up views of cities more accurate. A 90-degree left turn on the map is a 90-degree left turn on the street that you're driving down. The distortion is minimal when you're close up, but on a world map scale, cartographers rarely use the Mercator. But the fact remains that there's no right projection. Cartographers and mathematicians have created a huge library of available projections, each with a new perspective on the planet, and each useful for a different task. The best way to see the Earth is to look at a globe. But as long as we use flat maps, we'll have to deal with the trade-offs of projections. And just remember, there's no right answer.
Model of the so-called geoid. To understand this geoid, we need a bit of imagination.
If the planet would be covered completely by water, the gravity field inside.
Okay, so now I just got to stop this for a little while because it's, all of a sudden one guy says there's no right answer, the other guy's talking about this geoid. What are they talking about? Well, we know that Mercator projection is what you have on your cell phone, and that's what I have on these maps. So I have to be careful how I'm measuring distance. I can only measure distance along the vertical lines, and if I wanted the distance to be correct. So what the ellipsoid, that the GPS, the satellites use this ellipsoid. So they convert the ellipsoid on this chart is shown, you see it's number 2 here. So that's the dashed green line is the ellipsoid fit to the Earth. So it isn't a question that there's no right answer or there's multiple answers. If I need to know if I'm going to clear this mountain over here at number 4, I need to know the relationship between the GPS ellipsoid and the cartographer map that I'm using. So if I have a hiking map, or a hiking map which is not the sectional, I have a hiking map, and it tells me that I want to use my GPS with it, I have to have a conversion from the ellipsoid into that hiking map that I'm using. Now, most GPS receivers like Garmin, if you buy a GPS receiver, have those conversions in it. You put the type of map you're on. But if you're out for a weekend, say you're a doctor out for a weekend and you're using your iPhone map up in the mountains, right? You could be up to 2 to 3 miles off because you are receiving GPS coordinates based on this green line, and you're actually over here, right? Because you need to make that conversion. So this has killed people. People have called 911 helicopter flights to come get them because they couldn't find out where they were. So you must make that conversion. We've actually bombed in the Grenada incident before you were born, probably. We actually bombed a hospital instead of a barracks in Central America because the F-16 pilots were using sectional maps instead of GPS coordinates. So it's very serious. Now this geoid, what's that? The geoid is this, right? And the geoid is how water would end up looking if you allowed it to flow, if you didn't stop it. If you allowed water to flow through our mass distribution of the Earth, it would look kind of weird like this. Well, what's that used for? Well, that's used for inertial navigation or for building a house. If I want to build something perpendicular to the ground, as far as the weight goes, I want it to be perpendicular. I want it to be perpendicular to the geoid, because that gives you my flat plane surface. So but sometimes the analogy of water is hard to understand. So sometimes the mathematics is best. So the geoid actually is defined where the magnitude of gravity is 32.17 feet per second squared. Like, it goes on 5 or 6 decimal places, but basically at 9.8 meters per second squared, or 32.17 feet per second squared, wherever that's true, that's where you are in the geoid. And look how screwed up it looks. Why does it look so screwed up and dented? Well, because the mass distribution of the Earth, there's a Grand Canyon out there. There's the Alps, right? There are the Himalayas out there. So that if the water would allow it to flow, it would flow and look kind of goofy. And that system is used by what's called inertial navigation systems. So all military aircraft, in addition to GPS, which it's a radio, it can be jammed, it can be shut off, but you can't jam inertial navigation system, because inertial navigation system navigates with respect to the geoid. And 0 feet MSL, 0 feet MSL, regardless of the tides, is defined by that geoid, and the geoid you see is number 5. So that's what he's talking about here as he goes on. So you can see there's 3 models of the Earth. There's a sectional projection, a Mercator projection. There's the ellipsoid model that GPS uses, and then there's a geoid model, which is used by inertial navigation systems. Or if you're building a house and drop a plumb bob, when I drop a plumb bob, right, that's how I'm going to build my house level. It's going to be, that plumb bob is going to be perpendicular to the geoid, not to the ellipsoid and not to the ground. Interesting stuff, isn't it? Yeah. So GPS positions and velocities are relative to a mathematical ellipsoidal Earth called the gypsoid. They're called the ellipsoid. Inertial guidance systems, INSs, positions and velocities are relative to the geoid.
Or the gravity field of Earth would shape the sea surface like that. If we had no land masses, nothing, the sea surface would look like the geoid.
This model is widely used by all kinds of scientists. It's been calculated previously, but never with the precision that we can see now. This global sea level reference will be used worldwide as the 0 level of heights. This is very important for GPS navigation and major engineering projects. So the scientific world has been...
So mean sea level, 0 feet in your standard atmosphere that you dial in on the standard, if you're flying, if today's a standard atmosphere, you dial 2992, mean sea level 0 feet is at the geoid where gravity is equal to 32.17 feet per second squared, out to 5 or 6 decimal places. All aircraft heights are measured from mean sea level as determined by the Earth's geoid, the gravity value at the Earth's geoid surface. The geoid reference worldwide is where the magnitude of gravity is 32.17. That should be feet per second squared. I keep forgetting to fix that. Hey, this is normally the break time. That's okay. We're doing fine. So this is actually this is from week 9. I'm just going to put this off, but so you don't have to know anything on this chart except for the red things. So navigation is position, velocity, and time, and we get all 3 of those from GPS satellite navigation. We get all 3 of we get the position and the velocity relative to what? Relative to the geoid, or I mean, relative to the ellipsoid, If I'm using an inertial navigation system, I don't need any of this stuff, and I get my position and velocity relative to the geoid. So this is a mistake also. It says a WGS geoid. Yeah, man, I keep finding these mistakes. That should be ellipsoid. Oh, man. Don't worry about anything on this. This is from week 9. I don't know if we'll have time to cover this stuff or not, but it's very detailed. The other cool thing, though, is that the GPS, your cell phone, does give you time. We all use GPS time now. Now you have mountain zone time, east zone. You have different time zones, but the actual seconds and about from midnight, the actual reading in seconds is all GPS time now. Well, let's go back to a heading. We haven't talked about the heading indicator. So I did mention that your heading on the map, the heading on the map depends on the angle, right? The angles are preserved on a Mercator projection. But what if I'm flying magnetic heading? Do I have to make a correction? And the answer is yes, you do. So if I were to go to San Luis Obispo Airport, let's say I were to go to San Luis Obispo Airport, and that's my magnetic heading indicator. So I'm heading right now 140 degrees. So this is 0 degrees is like so going up. 90 degrees is to the right, and 180 degrees is down. So 140, I'd be heading about this way, right? 140, about like that arrow. But if I was lined up with the runway, this heading would change to 290 degrees, because that's the magnetic heading of the airport. So, but if I were to go on my sectional chart and I could measure 290, I would not be lined up with the runway on my sectional chart. the runway on my sectional chart would be 303 degrees. It would be 303 degrees. So why the difference? Why do I have a 13-degree difference? Well, I look over here, and there's this dotted line, and you probably can't see it, but this says 13 degrees east there. That says 13 degrees east, and pretty close to San Luis Obispo. That tells me that the difference between the true course and the magnetic course at San Luis Obispo is 13 degrees. So I have to subtract 13 from my true course to get 290 degrees magnetic heading. And that's what I see in the cockpit. I see 290. On the map, it's 303. Yeah, pilots have to remember that. They have to remember that and which way it goes. So why is that? Why is that physically? Well, the true course is relative to the Earth rotation. The Earth is spinning, and the axis it's spinning about is true north. That never changes. So the 303 degrees is always going to be 303 for our runway. However, the magnetic north is moving around. It's moving around. It moves about 30 or 40 kilometers a year. So it moves all over the place. And so the variation is changing. And how much does the variation change? Well, I don't know. Right now, they say it's around 13 degrees. Maybe in a few years, it'll be 14 degrees. Maybe it'll be 15. So when the variation changes such that the runway heading, say the actual magnetic heading is going to be 295 or 285. Say the variation goes from 13 to 17 or 18. Well, then they'll change the runway heading. So in other words, right now there's a big 29 painted at the end of the runway for San Luis Obispo. They'll change it to 30. You know, they'll change it, or to 28. They will change it every time it moves by more than 5 degrees off of a cardinal heading. So this is what it looks like on a section. I tried to show you. You probably couldn't see it, but if I could blow it up, you see it's 14 degrees east. Now, this is not San Luis Obispo. This is some other place out in the west. And over here on the right, there's the North Pole in the bottom right. You see the North Pole over here? That never moves. That defines your true course. So when I measure lines and distances on my Mercator possessions, on my Mercator projection map, I always get the same number relative to true north. But look at the magnetic north. Look at how it's moved over the years, right? And I don't know where they get the information from. This is from our government agencies. So, and it's moving about 30 kilometers a year. So the variation changes, and they tell me that it's going to flip. The poles are going to flip again. They flip about every 12 million years or something. They flip. Could look that up, but that's why magnetic and true courses are different in the cockpit. Okay, so what does all this mean? What does all this mean? Well, all these mathematical models, right? Now, if I were to teach the standard atmosphere with equations, if I were to teach it that way, I know about 5 minutes into that, you say, well, I'm never going to use this. Why would I ever use these equations? But if you look at it from the point of view, I'm sitting in an airplane or I'm flying an airplane, I need to know where when I'm at 212 feet on my altimeter reading, I need to know I'm on the ground at San Luis Obispo. I need to know that. Yeah, then you can see, well, I need to know. So this is, we're looking at the practical applications of mathematics. Everything we do now in an airplane pretty much is modeled, it's virtual. It's synthetic. It's either an ellipsoid model from GPS or a geoid model for inertial navigation or a Mercator projection of some kind. And it's all automated. So here's a fighter cockpit, and it shows you, and you can see in the center, you can see the attitude indicator. The heading is on below. And here's a God's eye view of a map that's presented to the pilot. And this is all weapon information over here on the right, system information on the sides. So avionics automates everything. And sometimes that automation, if you don't understand the basics that we've covered today, can be confusing to the pilot, very confusing. Even if he does understand, it can be confusing. So here's a civil cockpit. It's called a glass cockpit. And it's got an MFD, multi-function display, an MFD. Moving map, electronic gauges, heads-up display, right, which is not shown here. And but some things always stay the same. So look at the gear handles right here. It looks like a little wheel. That stays. It always stays the same. And here's a flap. The flap panel looks like a little flap. So regardless of how automation occurs, the gear and the flap still looks like instruments that they used to be on the Boeing's first on the first airplane that had a gear and flaps. But what happens is, if the automation, you can have two philosophies. you can have what we call the Airbus philosophy. Automation is good. Minimize the pilot input. That's the Airbus philosophy. The Boeing philosophy, believe it or not, traditionally has been never automate to the point where the pilot is not in control. The pilot has ultimate command. Those are the two philosophies that we'll see. And as automation develops, automation is going to develop regardless of those two philosophies, because it does lower the accident rate, because it tends to, as it automates and helps the pilot, the accident rate goes down because the pilot is still the most significant cause of most accidents. The problem is we don't really know what's going wrong then. You saw how the confusion of the pilots had in the 737 MAX. They become very confused. The pilot, this is what we used to joke about. What's it doing? The co-pilot, I don't know, doing it again. Gee, what could go wrong with that? So there's a good and a bad and the ugly with automation. So I'm going to show you examples of each. The good. We'll start with the good. We'll start you with the Airbus philosophy and show you. I'll try to show you anyway what that looks like. If I can find it.
Aircraft is an A330 built by aerospace giant Airbus. Though there are 700 in service, there hadn't been a single passenger fatality until Flight 447.
We'll talk about that flight.
This history of reliability rests on a highly computerized flight control system.
They're highly automated. They're some of the leading edge technology in aviation even today.
Powerful computer systems are designed to control everything from airspeed and altitude to turning the aircraft. The design philosophy that automation improves safety. In a flight simulator,
V1, rotate.
Veteran
V1,
pilot
V1.
Martin Alder demonstrates the features of these computer systems.
Gear up. In a conventional airplane, instead of this side stick, I'd have quite a big control column here, but you need plenty of leverage to apply the mechanical forces you need to move the control surfaces to control the airplane.
In a conventional airplane, the pilot pulls mechanical levers to operate a hydraulic control system. But on the A330, this heavyweight gear is replaced by an electronic system called fly-by-wire. The pilot tells the flight computer what he wants to do, but it is the computer that translates this intention into action and executes the maneuver.
So if I want to go to the left, stick to the left. Round to the left.
The flight computer adjusts the control surfaces and the aircraft turns left. Maneuvers like this cause the A330 to lose altitude. So the advanced computer compensates by increasing power and pitching the nose up to provide the right amount of lift. The pilot does nothing.
I take my hands off, and there we are. It's flying round. Vertical speed 0, 25 degrees of bank, 240 knots. It's going to fly around at 25 degrees of bank. Keep doing this until we get bored.
The flight computer won't carry out any pilot command that endangers the safety of the aircraft.
If the pilot were to lose control for some reason, the system would save the airplane.
Now that's the you can tell these guys are Airbus people, right? Pilot would say, you know, it's just flat not true. Okay, so it's hard to watch this stuff, but you learn a little bit about it, about this stuff. So that was the good. So let's look at the bad. If we look at the bad, we have to look at almost all military aircraft. So this is pretty much all military aircraft. This is the F-22. And you might remember the F-22. That was Mark Morgenfeld, the guy that flew the Lockheed entry for the F-35. Morgenfeld. So, let's look at the ugly now. If this has happened to every airplane that has been built. So here's a Swedish airplane, the Gripen. So every foreign airplane that's been built, every foreign fighter that we know of, has had this problem. This is a new airplane. So you see what it says here, if I can get my thing going again, my spotlight. What it says here is that this is a Saab, it's a Gripen, that's called a Gripen airplane, and it's a pilot-induced oscillation during flight test landing. So almost every fighter that's been built has had this happen, right? So what is that? What exactly is that? Well, let me explain what happens. And the same thing happened to Morgenfeld on the F-22. It was incorrectly described in the video that I showed way back when. So the pilot's in the, he's going to go around. He's going to go around. He's going to raise the gear, raise the flaps, you know, and he's going to be moving hydraulic pressure to change the stabilator in the back to pitch up. That all of that takes a lot of hydraulic pressure. So when you're moving the stick a lot and you're doing a lot of things with the airplane, you're taking a lot of hydraulic pressure. What happens when the hydraulic pressure gets low or goes to zero? Well, things stop moving. Everything freezes until the pressure pumps build it back up again. Well, when that happens, the pilot's moving the stick and nothing's happening to the airplane. So you get this what's called a pilot-induced oscillation, or PIO. And it happens in all airplanes. It happens in all big airplanes, except in the big airplane, the pilot seldom is doing this except in landing. So which is worse. That's when you have the pilot-induced oscillation in a big airplane like an Airbus on landing. Space shuttle, same thing. So to stop that, you have to either take the pilot out of the loop or limit what he's doing. Now the F-22, he had the thrust face engaged. He was raising the gear, and he just had too much hydraulic pressure, and the aircraft couldn't keep up with it. So it was called a computer glitch in the first video I showed. It wasn't. The computer's operating perfectly right. It's just that something had to limit the pilot from making hydraulic pressure go down to zero. So there's a company called Calspan at Buffalo, and they're in business by fixing these in aircraft that are developed all over the world. So that's the good, bad, and the ugly of let's see if I can go back now to where we were. Share this. So that's the good and the bad and the ugly. And if you want to watch the whole videos, those are the sites that I was just tied into. Okay, now let's go back and look at the Airbus. All right, here was the Airbus. Oh, this is the first airplane. Before I get to the Airbus, this is the first automated airplane in France, the first one that was built.
Aircraft manufacturers have tried to fix that problem by designing the pilot out of the cockpit. This is the first fully automated plane, flown by a computer.
Oh no.
So fortunately, nobody was hurt. The crew that was on it got out, amazingly enough. They didn't get hurt, which is, to me, is amazing. So when you automate, you can have serious problems. But the safety record is going to get better. The aircraft accident I'm going to show you now is the Airbus. And I'd like you to focus a little bit on the side stick. Remember the guy who was talking how cool that side stick is? Yeah, and it will not let the pilot do anything dumb or stupid, right? That the airplane will not let it. So focus on that for that part of the automation for this accident. And the other thing I want you to remember that's not shown here is, had we not found this airplane in the Atlantic Ocean, had they not found it, we would have no idea what caused the accident. None. That's the problem with automation, is that your accident rate, it's a paradox. Accident rate gets better, but there's no one to blame. There's no one. It's a systemic accident. Who do we blame? We blame this maintenance guy out here. He's living in Bolivia somewhere. So that's what you have. You have better accident rate, but unknown causes. Can we accept that? We want to blame somebody. Hey, we want to blame you for doing this. We want to blame you and fix it. But as you automate, that becomes more and more difficult to do.
Final word on the crash of Air France Flight 447. It happened 4 years ago today, June 1st, 2009. The Airbus jet carrying 228 people vanished over the Atlantic on a flight from Rio de Janeiro to Paris.
It took years to find the wreckage, recover the plane's black boxes, and solve the mystery. But when they did, the answers changed the aviation industry forever. Here's Mark Strassman.
4 years after Air France Flight 447 disappeared over the Atlantic Ocean, experts have pieced together what they believed happened on board the airliner that June evening. Detailed analysis of the reported cockpit transcripts points to a perfect storm of problems, including weather, aircraft malfunction, and pilot error. But some experts say there was another contributing factor, the very design of the Airbus cockpit.
Would Air France 447 have had the same disaster if this cockpit were a Boeing instead of an Airbus?
I think it would have been much less likely to happen in a Boeing because the control wheels are large, they're obvious. I think it could hardly have been missed.
When's the last time you were on one of these? To help us break down and understand what happened on board Air France Flight 447, CBS News aviation and safety expert Captain Chesley Sully Sullenberger took us into an Airbus simulator.
This is going from neutral to full nose-up command, full aft side stick. That's it, right there. That one little movement.
That small movement on the Airbus flight controls, or side stick, raises the nose of the plane and instructs it to climb. Pilots rarely perform the maneuver at high altitudes because it can be very dangerous. But that is exactly what one Flight 447 pilot did. Around 2:05 a.m., when the Airbus A330 was flying through a storm system, all three of its speed indicators stopped working. As a result, the aircraft's autopilot turned off. With the captain on break, the two co-pilots were forced to fly the plane manually. The least experienced pilot, 32-year-old Pierre Bonin, was in the right seat and said, "I have the controls." Co-pilot David Robert was in the left seat, and even though considerably more experienced, he let Bonin fly.
Theoretically, it was possible to still fly the airplane under those conditions.
Challenging, but manageable.
Yes.
Although they lost the autopilot and speed indicators, they were flying normally and safely. But then suddenly, and without Robert knowing, Bonin does something almost inexplicable. He pulls back on his side stick and raises the nose of the plane. That causes the aircraft to fall, and the stall warning sounds.
That's the alarm.
Stall alarm. Over the next 4.5 minutes, the stall warning will sound 75 times. But strangely, neither pilot will mention it. And unbeknownst to Robert, Bonin will keep the nose of the plane up almost the entire time, exactly what he shouldn't do, a decision that experts still can't understand.
It's difficult to explain that. I just don't know why he did that.
And there's nothing to you that makes sense on any experience or intellectual level about pulling back when you should push forward?
No.
Nothing at all?
Because of Bonin's actions, the plane is attempting to climb, but is actually losing altitude. Robert appears to have no idea the nose is being lifted when he says, "What the hell is happening? I don't understand what's happening." If he had known what Bonin was doing, Robert could have conceivably solved the problem very easily at this point.
So you're sitting where Bonin was sitting, and he starts pulling back.
Right.
Sullenberger showed us why he thinks in this situation the design of the airplane helped keep Robert in the dark.
And it's a subtle movement compared to more traditional airplanes.
And unless I happen to notice you visually doing it, I would have no way of telling that it happened.
Because your side stick is not linked to mine. When I move this one, that one never budges.
By traditional airplanes, Sullenberger means those built by Boeing. There are only two major airliner manufacturers in the world, Boeing and Airbus, and the two have different cockpit designs and philosophies. The main difference, Airbus uses side stick technology, Boeing uses a yoke.
In this airplane, you have a big control wheel. It's right in front of both pilots.
We sat down in a Boeing 747 simulator to see the difference.
They're mechanically linked. They're not independent. So if I move mine, yours moves in unison.
Had he been pulling back in a Boeing, how would it have looked?
Like this.
And on my side, it's in my lap.
Yes.
Robert would clearly have known what was happening if this was happening in a Boeing.
I think it would be obvious.
Yeah.
Airbus, however, has never wavered in their public support of the cockpit design. At 2:10 a.m., 5 minutes after the autopilot disengaged, the Airbus A330 continues to lose significant altitude as the captain re-enters the cockpit and says, "What the hell are you doing?" Bonin, the least experienced pilot, continues to hold back on his side stick, but still doesn't seem to understand what's happening. "We've lost control of the airplane," Bonin says. Robert tells the captain, "We've totally lost control of the plane. We don't understand at all." Almost a minute later, as the plane is now just 10,000 feet above the surface of the ocean, Bonin finally reveals the crucial information they've needed. He shouts, "I've had the stick back the whole time." Robert seems to instantly realize what's going on. He jumps in and says, "Give me the controls, give me the controls." But it's too late. About 40 seconds later, the two co-pilots say what will be their last words. Robert, "Damn it, we're going to crash. This can't be happening." Bonin, "But what's happening?" 4 seconds after that, the voice recorder cuts out.
It's clear that the pilot of Airbus have to work as a team.
Robert Soulas is the president of a victim's family support group. He lost his 24-year-old daughter Caroline in the crash. Her husband of just 2 years was a flight attendant on board.
I was alone on the earth. Nothing to speak, a lot of questions with no answer.
228 people lost their lives that night. After analyzing debris and examining remains, experts suspect passengers likely didn't know what was going wrong until they hit the ocean's surface. A tiny bit of solace in one of modern aviation's biggest disasters.
We don't want that the victims are dead for nothing.
Earlier this year, after analysis of Flight 447 and other incidents, the FAA issued a safety alert for operators, encouraging pilots to have more experience flying without the use of auto-flight systems. The agency believes maintaining and improving the knowledge and skills for manual flight operations is necessary for safe flight operations. But some industry experts say, although that's a step in the right direction, it's not enough.
If we only blame the pilots, we will not have changed any of the fundamental underlying conditions. We won't have done our best to prevent this from happening again.
This is the safest period in the history of commercial flight, and yet Flight 447 simply fell from the sky. For CBS This Morning Saturday, Mark Stroud.
Final word on the crash of
So how do you justify what happened? How do you justify what happened there? It's hard. It's hard. And the people, of course, had no idea in the back. Had they not found that airplane months later after the crash, they would have no idea what happened. And of course, the real pilot error was the Robert in the left seat. That was the pilot error. As soon as they had a problem and the pitot-static system went bad, probably from a lightning strike, but we don't know what hurt the automated system. He should have told the new co-pilot to get out and go get the captain up. He's slipping in the back. Go get him. Bring him up here. That would have probably solved the problem. But you saw, because the sticks weren't hooked up, it was just a mess. And it boils down to what I've been trying to say. You know, this simple formula up here, right? This very simple formula that we've been flying. Lift pressure over dynamic pressure. If you understand how that impacts flying, almost none of these accidents would have occurred. And when you get to the systemic level of accidents that we just, this last one with Airbus that showed you, what he said, this is the safest time we've ever to fly. But everybody's kind of afraid to get into it, because when you have an accident, it can be horrific. Look at the Malaysian airplane that we still don't know disappeared flying around the off the Indian Ocean. We still don't know where it's at. So these are difficult questions, difficult problems, and they demand lots of give and take. Lots of checks and balances have to occur. That's pretty much, and I should give you one little personal incident. I got a kick out of this one. Here's singer Sheryl Crow. I don't know who Sheryl Crow is. You probably do. But she has a Tesla, and she was in the Tesla, and everything went black. So she started calling people. I guess you can call people in a Tesla when your car goes black. And Elon Musk answered her. Elon Musk came back and told her what to do. And I was flying the RV. You know, Cal Poly has an RV7, so I was flying it once by myself, and I was flying it, and everything went black on the screen. Now in the RV experimental, it's everything. I had no engine instruments, no attitude information. All I had was my hearing. I could hear the engine and see outside. So I got the airplane down, and I'm taxiing in, and I'm wondering, gee, the whole system went bad. How could that happen? And what happened was I had inadvertently selected night. I inadvertently had selected nighttime. So the screen went dark because it was a nice day. It was a beautiful day. But so that interface between the pilot and the automated system that's being generated, that interface is crucial. And it's occasionally inverse Murphy's law will come in and you will have an accident. So that's going to take us to the quiz. Again, here for this week's quiz, the first 10 questions have 15 choices, or actually I have 20 choices. So there's 20 choices on today's quiz. The quizzes get a little bit harder. Then there's extra questions, pretty much about the altimeter. So I wanted you to, the reason I focus on the altimeter is because to emphasize that your altimeter is a mathematical thing, right? I kind of turned it around and made it a stick for a demonstration, but it's a mathematical thing. So you have to select the correct reference for the day you're flying in. You have to select that. And physically, it means that if I were pulling out of a vat of mercury, I could pull 29.92 inches out on a standard day if I was at 0 feet MSL as defined by the geoid. So here's an actual case where the altimeter setting is 2836, I think. So you're 1.56 inches off. You're 1.56 inches, and that's about 1,560 feet. So if I have 2992 set in, when I measure, when the altimeter feels or measures 2936, it's going to think it's 1,560 feet up. So it's going to think it's up here, but it's actually down here. And you can see why then high to low is dangerous. So you want to have it, the altimeter should be aligned at all low altitudes where contact with the ground is a problem. Now you get above 18,000 feet and everybody puts 2992 in, because up there you're not worried about hitting the ground and you're just worried about hitting each other. So your separation is based on altimeter pressure, but everybody has 2992 set in. And then we talked about these different surfaces today. We talked about the ground surface. Let me see if I can get my thing going again. We talked about the ground surface over here, and then we have the ellipsoid, which is the green dashed line from the GPSs, and we have the geoid, which is number five, and that's where gravity is 32.17 feet per second squared, or 9.8 feet per second squared. And then, of course, here's an example problem of setting the wrong thing in the altimeter setting, and how you'll be lower than the altimeter is reading. You'll be lower. And I think that's about does it. You don't have to worry about any of this stuff. Just make sure you understand what the red letters mean or what they indicate. This is all stuff from week 9, which we may or may not get to. I know you're hoping we don't get to it, but none of this will be on the midterm exam. And then here is, I don't know if you can see, let me just finish this class off by showing you, yeah, I can do that. Look at the altimeter setting here, 2986. See that? 2986. So this guy has got the altimeter setting. So he thinks that the altimeter will read 0 feet. That will read 0 feet where? That'll read 0 feet when at the 0 feet MSL, mean sea level. So how high is his field? Say his field is 212 feet. So when this altimeter reads 212 feet, he will be landed. He will land on it. Notice that you can actually, if you're sitting at San Luis Obispo Airport, you can put 212 feet on your altimeter, and then you can read out the atmospheric pressure from the window. So that takes care of that. And I think we're within 1 minute of quitting time, so I'm gonna open it. I'm gonna stick around, but I open up for any questions. If you guys got any questions, you can on today's content or the quiz or what's due on Sunday, your groups, you can go ahead and fire away. So class is over. Thanks for showing up, everybody. I appreciate it, and I hope you guys have a great weekend. Don't drink any mercury. Bye. The second hour, my granddaughter was banging on the door, so she probably realized. I was kind of hoping she'd come in. I could introduce you to her in real life, but she didn't come in. Will there be a study guide for the midterm? Yeah, everything that's written on the ViewGraph notes is your study guide and the quizzes. So the answer is yes, but you have the study guide already. I think I've covered all these questions. Hey Aubrey, I see you're still on. Did you get your groups all set now? I sent you an email fixing that group. Are you happy with? Okay.
Thank you so much.
No problem. I just want to make sure that everything is good. Any problems with anything? Then don't forget Sunday night. I try to be online at 8 o'clock Sunday night after 60 Minutes CBS show. We watch that, and then I'll be online. I had a couple panic emails last Sunday. All right. Well, again, thanks for showing up. Feel free to email me. Have a great weekend. I'll see you next week. Bye-bye.